Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face Trending List, published on November 21st, 2025, about 4 days ago. It introduces a single model that both plans robot actions and predicts future images, reaching about 97% success on the Lee-Robo simulation benchmark without pre-training and boosting real-world Lee-Robo success rates by 50%. The paper is titled RynnVLA-002, a unified vision language action and world model. And as we will see later, the results are really impressive for robots that need to both imagine and act in complex environments. Also, the author shared a full GitHub repo for RynnVLA-002. You'll find the core Python code, configs, and training pipelines for both the VLA and world models, a model zoo with ready-to-use checkpoints, detailed Lee-Robo and Lee-Robot data prep scripts, plus evaluation and inference scripts to reproduce their results. Alright, Figure 1 contrasts 3 ways to connect perception and action, showing why the unified design matters. This figure shows 3 panels comparing a plain vision language action model, a pure world model, and the proposed action world model. The left panel has a VLA model that understands images and can output actions, but it cannot predict future images or reason about actions internally. The middle panel shows a world model that understands and generates images from actions, yet it cannot directly output actions for control. The right panel combines all 3 tokenizers so the action world model can both understand and generate images and actions, giving the robot imagination plus decision-making in a single system. Figure 2 explains how RynnVLA-002 actually processes information to both act and imagine the future. The left side shows the vision language action stream, where text, robot state, and images pass through tokenizers, then the shared backbone, and finally the small action transformer that outputs smooth, continuous, or discrete actions. The right side shows the world model stream, where text, images, and actions are tokenized and used to predict the next image frame. Because both sides share the same token space and backbone, learning to act and learning to predict future images strengthen each other. Figure 3 shows how changing the attention mask stops action errors from cascading through the sequence. The left panel uses the default mask, where each future action can attend to previous actions, so a single mistake can snowball into many. The middle panel blocks that action to action attention, forcing actions to rely on text and images instead. The right panel gives the world model a mirror pattern, where future images depend on past images and actions, but not vice versa. Table 1 compares success rates on the Lee-Robo benchmark and shows that the unified model reaches top performance without any pre-training. This table lists many recent vision language action methods, whether they use pre-training, and whether they output discrete or continuous actions. RynnVLA-002, with discrete actions, already matches or exceeds most discrete baselines. The continuous action transformer version then pushes the average success rate to about 97%, slightly above all listed methods. This result means a single unified action plus world model can compete with or beat heavily pre-trained systems. Table 2 shows that the unified model holds up in the real world, even against heavily pre-trained baselines. This table reports success rates for 100 robot tasks, each with single target, multi-target, and distractor variants. RynnVLA-002, despite no pre-training, matches or beats GR00T and Pi0 in the harder multi-target and distractor settings. That pattern suggests the shared action plus world modeling especially helps when scenes become cluttered and goals vary. So to wrap up, the key idea is that a single model that both imagines future images and plans actions gives robots a big boost in simulation and in messy real homes. The broader implication is that unified world plus action models might become the standard recipe for embodied agents. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.